Hey everyone, we'll get started. Thanks so much for coming. It's really great to see so many people here after our long hiatus. Some people may have known Astronite from before COVID. If so, welcome back. If you're new, welcome for the first time. So the way Astronite goes is we're going to do a talk here, given by a guy, and then afterwards we're going to go up to the top floor of Campbell and we have a telescope set up. Look at things like the moon, different nebulae, stuff like that. So yeah, so introductions. So this is Guy. Guy earned his bachelor's of science in physics from Ben Gurion University in Israel. Afterwards, earned his master's and PhD in astrophysics from the Weizmann Institute in Israel, and recently came here as a postdoc to join us doing some research working with Professor Josh Bloom. Research-wise, Guy works mostly with building software for astronomy. He also researches fast variables in astronomy and also some instrumentation stuff, so building different astronomical instruments. So without further ado, take it away.
Okay, thank you. It's really nice to see everybody in person. I'm excited. I haven't done that in a couple of years, so this is fun. I first gave this talk at a science fiction convention back in Israel a few years ago. And I kind of went on this direction because I was infiltrating a little bit because this is mostly science. I was going with the angle of this used to be science fiction and now it's not. So that's the connection I'm making here. So if you see some science fiction references in the slides, I hope you recognize them. Also, I'm going to give you a chance to download the slides in the end if you want. The reason is there's lots of references and links to more reading if you find it super interested in some of the topics. I can't go into detail on a lot of these things, and it's a shame. So if anybody wants, in the end, you'll be able to get the slides as well. Okay, so life on other planets. Right, so we have a few big questions. How did that life actually begin on planet Earth? When did it begin? How it actually happened? Can we find life on other planets? How can you actually do that? And intelligent life, where is everybody? So these are big three questions I'm going to talk about today. So let's start with stuff, with this basic equation. It's called the Drake equation. Frank Drake in the 60s worked on a lot of stuff for searching for extraterrestrial life. And the main idea of this kind of equation is that you don't really know what any of the numbers mean, what their values are exactly, but if you make kind of rough estimates, you can sort of figure out, is this plausible? Are there 1,000 civilizations in the galaxy right now? Are there 0.01 civilizations in the galaxy? What's the rough order of magnitude? And this is the main reason we have this thing. So how many stars do we have in the galaxy? How many of them have planets? How many of those planets, how many planets in each system on average? How many of them are Earth-like and can harbor life? And if they do harbor life, what is the probability of being intelligent life? And if they are intelligent, what is the probability of developing communications? And you multiply that by the lifetime of the average culture, and you kind of get an estimate for how many such cultures we have in our galaxy. And we're going to see that a lot of these numbers we actually do know now. Some of them are harder to pin down, but some of them are actually not science fiction anymore. We can actually answer these questions. In the 60s, when this equation was written, people kind of made fun of it because they're saying, oh, well, you take a bunch of numbers that you don't know the value of any of them and you multiply them. You can kind of get any number that you want out of it. Which was true, I guess, maybe 20 or 30 years ago. But now we're starting to get more answers to some of these numbers. Okay, so before we start, I don't know how many of you have been to astronomy talks, how much background you have. So I'm going to give some basic numbers. Okay, so a star is something that actually produces light, right? A planet is something that's not producing light. It's orbiting around a star usually. So the sun is a star, and the Earth and Jupiter, for example, are planets. Moons are even smaller and they orbit around planets. That's the definitions of the different stuff we're going to talk about. Light years, which is kind of a scale that people use a lot in astronomy and like to throw it around, but you never get a sense of how big that actually is. So if you take the entire solar system's width, including the orbit of Neptune, and you put it in the millimeter bar of this 1 meter ruler, I'm sorry, this is in meters, but if you can imagine, this doesn't go all the way to 12 millimeters, it goes all the way to a meter. then that will be about 1 light year. So you can kind of imagine this thing is much, much bigger than the solar system. And this is just 1 light year. And as for our galaxy, we have about between 200 and 1,000 billion stars. When I say billion, I mean 10 to the 9. There's a similar number of galaxies in the universe. As you can see from this very, very small patch of sky taken by the Hubble telescope, you can see most of these things are galaxies. So just everywhere you look in the universe, there's literally billions and billions of galaxies. And if you want to talk about sizes, then the nearest stars to us are about 3 light years away or 10 light years away. The entire galaxy is tens of thousands of light years in diameter. And the nearby galaxies are already millions and tens of millions of light years. So this is so far away from us that I'm mostly going to talk about our galaxy, because even if we do somehow find life on other planets, on other galaxies, just communicating is going to be millions of years in each direction. So it's kind of not practical, even if we do somehow figure it out. So most of what I'm talking about is between tens of light years and thousands of light years. That's kind of the scale of what we're talking about. And the entire observable universe, just so you get a sense of the size, is billions of light years, a few tens of billions, depending on how you count. Any questions about this so far? No, right? Basic stuff, right? So let's talk about ages. So the age of the universe, 13.8, again, depending on how you count. Age of the Milky Way is just a little bit smaller than that. So the galaxy formed a little bit after the Big Bang. And the solar system, our humble little place in the galaxy, is only 4.5 billion years old, approximately. And the Earth only cooled to have liquid water around 4 billion years ago. So this is kind of the timeline that we have for what's going to happen on planet Earth. Yeah, so we're going to talk about, first of all, the first question is, how did life start? We want to know about life on other planets. We kind of want to get a feeling for how life actually works. So there were a few experiments in the 50s where people just put a bunch of chemicals, different chemicals that they thought used to exist on Earth before life existed, and zapped lightning into the water and added heat. And you can kind of get some of the molecules that build up life from these types of experiments. You can't get all of them. There's been many, many such experiments. And right now, if you read kind of the cutting edge literature about this sort of stuff, about how abiotic chemistry turns into biotic chemistry, people have pieces of the puzzle. They know how to make some of the amino acids that you need for life. They don't know how to make some of the processes. There's a bunch of problems. So we know a little bit. But kind of this philosophical question that you're thinking about is, how does actually something start? How does something so complicated like life actually begin out of just very simple chemical compounds? A lot of people have a hard time wrapping their mind around that. So here's a little thought experiment. You take black and white squares and you give them a set of rules. For example, if there are, I don't remember exactly, if there are 2 or 3 live neighbors, the live ones are the black ones, then you stay alive, and you're born if you have exactly 3 live neighbors. And all other situations, the cell dies. And if you put these very, very simple rules for on and off of these pixels, you can actually get very complicated forms of life. You can see this animated, right? So this thing actually generates these little floaters, and you can this kind of almost looks alive, right? And the rules of the game are really, really simple in this case. So you can imagine what happens if you have 3-dimensional space with actual molecules, and you have thousands and tens of thousands of chemical interactions that can happen even without anything living. And kind of you can philosophically make this leap just to say maybe there is some way for these very simple rules to allow you to have life to emerge, is what this philosophical experiment tries to show. And again, I don't know if we actually know how that happens. Some people are saying that actually it all started down in these underwater vents where these volcanic activity spews out different chemicals and heat, which gives the energy to start this whole life thing up. Some people are talking about shallow tidal pools, and the sun just beamed into it and kind of caused this chemistry to start up. There are some problems. As I said, we only have pieces of the puzzle. So for example, you need proteins to generate DNA and replicate DNA, but proteins are produced by the DNA blueprint, right? So it's kind of a chicken and egg problem. You can't have DNA without proteins, and you can't have proteins without DNA. So some people are saying maybe the RNA, which is kind of the thing that delivers the information from the DNA to the proteins, maybe that's the thing that started existing and then got more complicated and diversified into different roles. Some people are talking about something called metabolism first, which is super interesting. I don't want to go into it too much. Some people are sometimes asking me about panspermia, which means that actually living material got blasted off one planet inside like a meteor and then floated through space for millions of years and hit the Earth. And actually, some people are saying that living tissue can survive deep inside rocks that get blasted like this. But even if you believe that, it doesn't solve the original problem of how life started. It just means that it started on Mars and then got blasted to Earth or backwards or something like that. So I don't know if that's a real solution, but the bottom line is kind of disappointing. We don't know how life started exactly. We have a little bit of an idea of some of the pieces of the puzzle, but we actually don't know. But it's okay to admit the stuff that you don't know in science. But here's something that we kind of do know, is that when life started. So using microfossils, really, really tiny pieces of something that looks like it used to be living material get trapped inside different crystals. You can date the crystals using nuclear reactions, nuclear half-lives of stuff like uranium that's naturally occurring. And when the crystal forms, it traps a certain amount of these isotopes that you can measure measure their density, and you can figure out how long this crystal existed when it trapped this living fossil inside of it. So you have pretty good dating methods. And the real problem right now is actually figuring out if the thing that looks like a living organism that got fossilized inside this rock, which is microscopic, how do you know if it's actually a living organism or just some molecule that looks like a living organism? So it's not really clear, but and the further back you go, the more degraded the evidence gets. So it's very hard to tell, but the feeling I get from research these days is that it used to be like 3 billion years ago. Then people found older crystals from 3.5 billion years ago. And now they're talking about maybe even 4 billion years ago. So it kind of seems like the more we look for these fossils, we find older ones with micro fossils inside of them. So it looks like as soon as conditions were right to allow life to exist on planet Earth, as soon as it cooled down a little bit from from forming and from all the asteroids hitting it, liquid water formed on the surface, and almost immediately life started. So to me, that sounds like anywhere that is hospitable to life. I don't know exactly what that means, but anywhere that is hospitable to life probably has life on it, because it starts very easily. It doesn't take billions of years to start. Okay, so here's a timeline. I'm not going to go into all these things, but a few highlights, right? So Earth formed somewhere around here. Life begins somewhere in this range, so pretty early on. For a bunch of times, it's just very simple life. There's the oxygen catastrophe at some point, which just means small algae, blue algae, started to do photosynthesis. That means creating oxygen out of light, and that was great for them. They could just generate their own food from light, but it was pretty bad for everybody else who was breathing the methane and the other types of materials. And when oxygen gets to a high percentage like it is now, it just killed off everything on the planet almost. So only the organisms that can adapt to breathing oxygen, like us, our ancestors basically, they did a really great time, because oxygen is super useful if you can use it, but it was a catastrophe for all the living organisms that weren't used to oxygen at that level. That's a side note. Okay, so at some point you have the Cambrian explosion. We're going to talk about that a little bit later. And here, just life started to diversify, more complicated life forms. I call this complex life in air quotes. Here in the middle is dinosaurs. They have a big chunk of the history of the planet, actually. And then if you take this tiny little sliver at the end and you open it up again to the entire screen, let's call it 7 million years, right? And then a small part of that I'm going to call humans, again in quotes, because you can debate at what point you can call it a human or where the fossils are. So let's just say 1 million, just to make it easy. And then just to set the scale, we only got to this continent 50,000 years ago. I'm not talking about Columbus, of course. Agriculture, 10,000 years, somewhere here in this red pixel. And then advanced technology, only 200 years, which is much thinner pixels. So this is kind of a little bit depressing because if you look at it, most of the time there wasn't any intelligent life on planet Earth. Most of it, the time was actually bacteria. It's still debated if intelligent life is on planet Earth right now. All right, so here's like a small summary. Before the Cambrian explosion, about 500, 700 million years ago, the Ediacaran, it was kind of a paradise. There were no predators. None of the animals could move very quickly. They would kind of slide around the bottom of the ocean, the shallow oceans, and gather up like materials or whatever. They didn't chase each other or kill each other. It was all very peaceful. And there's very little actually evidence because all these animals were very soft. They didn't have skeletons or shells. So you only get evidence for this from mudslides that actually captured some of these things alive and just kind of imprinted. And you get the imprint in the mud because there's no bones. So it's very rare to actually find life, evidence of this kind of life. Then the Cambrian explosion happened. Just, I don't know why, but for a few million years, many species just appeared in the record. And they started hunting each other and they started developing armor and they started developing teeth to pierce that armor. And we're not sure what came first, actually, if it was the teeth or the armor. But in any case, the paleontologists win because now they have all this evidence of hard stuff that gets fossilized and can actually figure out what these species were like. And you can still see that these are pretty alien creatures, right? It looks nothing like what we have today. Yeah, I'm actually going to do, we're going to play a little game, okay? It's called Cambrian monsters, right? So I'm going to take a bunch of monsters from the Cambrian age, and I'm going to let you guess which one of them is not a creature that actually lives on planet Earth. Anyone want to guess? Yeah, what is that? They all look like spiders. This one? All right. Does anybody know what this is? Alien. Thank you. This is the face grabber from Alien. All right. What do you think? That can't be real, right? What do you think?
The top left is for Babylon 5.
Yes, thank you. He's the only one who knows that, right?
Is that hallucinogenic?
That is hallucinogenia. Thank you.
I knew it.
Yeah, this is a fossil. This is a 3D simulation of what this creature looked like. And this is the bad guys from Babylon 5. This one's easy. This one's pretty easy, right? All right. Okay. You recognize this one? This is older than Babylon 5, just so you know. It's the Star Wars thing where Boba Fett fell into it in episode 6, right? This thing actually was so bizarre that people found the tentacles and found the mouth and found the body in these fossils. And they were like, oh, look at these animals fighting each other. And then only when they found these 3 different parts multiple times in the fossil, they figured out that it's actually part of the same creature. It was so bizarre. All right, so that was just interlude. All right, so how do we actually find life? Okay, this is more of what I know about. So far, it's biology. I don't know anything about that. But let's talk about planet Earth. Okay, is it special? Is this the only place in our galaxy where life can exist? So, 20 years ago, people would say maybe. We don't know. So you have to be the right distance from the sun. You have to be in the habitable zone. Too far away, everything freezes. Too close, the water vaporizes. It's very hard to live. So we're kind of in the Goldilocks zone, right? You have to have an atmosphere that has nitrogen, oxygen, and carbon. Maybe you have to, I don't know. You have to have water. Water is really great. Everything just dissolves in the water. You can use it for so many things. Magnetic field maybe protects you from cosmic radiation, from radiation from the sun, particles from the sun. Maybe you need it, maybe you don't. So how many planets like the Earth actually exists around other stars? I mean, we know in the solar system there's only one place that looks like the Earth, but what about those billions of hundreds of billions of stars in the galaxy? And also there's a question, another philosophical question for you. Are we lucky? Right? Are we lucky to be living on planet Earth and not on a less hospitable place? So yeah, so some people say yes, but in science we kind of don't like this answer of us being special or put here by somebody, or that's kind of not the direction you usually think about when we're doing science. But again, this is philosophy. But some people would say they call this the anthropic principle. And they say that if we weren't living on planet Earth where conditions are so nice, and life wouldn't have developed here, and we wouldn't be here to ask these nice questions about astronomy and other planets and life. So, if we were some unlucky microbe to be born on a planet, without atmosphere, then, we probably wouldn't evolve very far. We wouldn't be intelligent. We wouldn't be having seminars and asking questions. So to be able to ask the question, you have to be lucky. So it's not really lucky. It's kind of a pre-required condition. And that's what we call the anthropic principle. We'll get that a little bit in the end. Okay, so let's start with the easy stuff. Can we find life on planets in our own solar system? It's close. We can see these nice pictures. So let's go through the list. Mercury, no atmosphere, way too hot. Venus, hostile atmosphere. All the spaceships that we landed, robotic spaceships, I should mention, that we landed on Venus melted after a few hours because of the high density heat and acid in the atmosphere. There's no water, except there's a little bit in the atmosphere. So now people are saying maybe in the upper clouds of Venus. Maybe, probably heard about this last year. Mars, maybe used to have water. Now its atmosphere is pretty depleted. Any water on Mars that exists is frozen most of the time. So probably not very good for life. Maybe in the distant past, it used to have life. So people are looking for that right now. And again, when I say people, I mean robots at this stage. Jupiter, Saturn, Uranus, Neptune, all gas giants. They don't have any surface to speak of. So maybe deep under this gas or some weird form of life, but definitely not something that we would recognize easily as life. So all these gas giants are not going to be a good place to find life. Let's talk about the moons of the giant planets. This is actually more optimistic, right? Some of these moons actually have conditions that may be conductive to life. So Titan, a very large moon of Saturn, has a methane atmosphere. So methane in that cold environment actually liquefies and it behaves a lot like water. There's actually lakes and rivers of methane on Titan. So there are spaceships that are scheduled to be launched to explore Titan more thoroughly in the next few years. And what they're saying is that maybe there's a different kind of chemistry based on methane that actually allows life to exist on Titan. Other options are Europa and Enceladus. Both of them have liquid water oceans under kilometers of ice. So there's a crust of ice, and then underneath there's many, many kilometers of water. And it's actually warmed up by the tides from their giant planet that they're orbiting. And here you can see Enceladus with what looks like volcanoes, but these are actually geysers of liquid water being spewed out from cracks in the ice. And in these gas plumes, there was a spaceship, the Cassini spaceship, which took this image. It flew next to those clouds and actually measured, I think that they have like, not living organisms, but like organic compounds, so maybe. There's a bunch of other moons that might also have these under ice oceans. So this is very promising direction to study, and a lot of people are actually planning to go to these moons and explore this further. But nothing obvious so far, no evidence of life yet. But let's talk about the big treasure trove, right? All these stars in our galaxy, all these billions and billions of stars in our galaxy. Do they have planets, right? So we call this an exoplanet for any planet that's outside our solar system. You want to actually measure them. So it's actually really hard to see exoplanets. A lot of times you see these really nice photos when you come to astronomy talks and you think that this is the sort of data we're working with. But of course, it's usually what you get is a noisy image with one pixel a little bit brighter than the rest of them. And you say, this is a planet. So this, for example, is our sun, and this is Venus. So in our solar system, you can get these nice images. When the star is, 100 light years from you, you don't get such a nice picture with any telescope. You have to look at alternative methods, right? You have, it's very hard to see them directly, although in some situations you can do it, very, very specific situations. Sometimes the star transits and hides the light of the planet transits in front of the star and hides just a tiny fraction of the starlight. You can kind of see how small Venus is compared to our sun. And if you measure the amount of light that goes in, at some point it drops for a tiny bit and then it comes back for a few hours. And you say, oh, all right, if this thing repeats every, half a year, then it's a planet. And this is actually a really good method of finding planets. You can also do it with a bunch of other methods. Spectroscopy I'm going to talk about. There's microlensing. There's a bunch of other things I'm not going to go into. So spectroscopy, I don't want to mention, what you do is you actually measure the different wavelengths coming off the star, and you can pick out specific lines, right? You know, this material produces this specific color in the spectrum. And if the star is moving towards you due to the redshift, the line gets a little bit bluer. And if it moves away from you, it's redshift, it gets a little bit redder. And then you can kind of figure out the speed of the star, if it's moving towards you or away from you. And if the star is moving back and forth from you, like in this picture, then that means that something is causing it to do that motion. So if the star has another star, like a binary star or a star and a planet, usually it's going to be a massive planet like Jupiter, then it actually moves the star a little bit because they're orbiting around the center of mass. And if it moves a little bit, you know, a few meters per second here, a few meters per second back, we can measure that today. In the past, you could have measured, you know, hundreds of kilometers per second or hundreds of meters per second. And then you can only find really big planets really close up to their stars. Today, the spectrographs get so good that you can actually measure less than a meter per second. And you can even see small planets that are wiggling their star back and forth. So this is one way to do it, but definitely, but this is hard. You have to take a spectrum multiple times. You have to, it's hard, it's very intensive. This is for direct detection. This is how it looks when you actually get really, really good data on the biggest telescopes in the world for stars that are pretty close by and that have really big planets that are relatively far away from the star. Then you can see these little spots and you can say, ah, this thing is a planet, this thing is a planet. And these, for example, are not planets, they're actually artifacts from the way the processing is done. So this is the kind of data you get at the best of the best conditions. So there's only a handful of planets found using this method. So, okay, so I told you 2 decades ago, all these questions were like like in the field of science fiction, nobody knew anything about this stuff. People in the 50s thought that sure, there's life on Venus, sure, there's life on Mars, and then, you know, started exploring these, and kind of stuff that used to be science fiction turns into science, sometimes in a disappointing way. Sometimes it's very exciting. So for example, in the 90s, people would find like one planet, found another planet using this spectrum. They have these really lucky to be able to measure these wobbles of these stars. And then kind of, it was going very slow. So the surveys would find a handful of planets every time. And most of the planets we would find were actually hot Jupiters. That means very massive planet, very close to its home star. And that's the reason is because this is how we were looking for them, right? It's weird. You think that giant planets should be far away from the sun, like in our solar system. But it turns out that there are some situations where these planets can actually move in close. And we used to find a lot of these because of the way we were looking for them, because of the spectroscopy method. You just see the wobbles much more for hot Jupiters than anything else. 2004 started to directly detect a few planets. And in 2009, the Kepler space mission actually went up and started to measure very, very well the light from a lot of stars and could see these short transits that we saw before. And Kepler started to find lots of planets. It found thousands of planets, like 4,000 confirmed planets right now. And actually, if you do the math about how many stars Kepler looked at and how many of them actually have planets, you see that if you count the number of planets, and lots of these systems have multiple planetary systems, it's actually about equal to the number of stars in the galaxy. So on average, there's a planet per star in our galaxy. So we didn't know that until 2009. So here's a few examples. This thing is very similar to Earth, is bigger than Earth around a sun-like star. This one has a bunch of planets that are close to their home star. This one has like 4 of them that are very close to the red dwarf. This is a very small, dim star, so they're actually in the habitable zone, or at least some of them. There's a bunch of examples. I don't want to get into them too much. Yeah, 2018, right? TESS went up to replace Kepler, which ran out of one of his gyros gave up, so it died. But TESS came up to do something similar to Kepler, only Kepler would look at one point of the sky and actually map all the planets in that patch. And TESS is actually mapping the entire sky, but only for stars that are close to the solar system. And the reason is that they're thinking, if we find planets that are close by, we will be able to point our big spectroscopes at them and actually measure the composition of the atmosphere and stuff like that. And you can't do that for very distant stars. But if the stars are close to the solar system, and this is what TESS is doing, you might be able to actually follow up and see if there's life on those planets. So here's a few more examples for exotic types of planets that we know about. TRAPPIST-1, actually not found by Kepler, found by a ground survey, but they found a bunch of planets. And these planets are all inside an orbit that's closer to their home star than what Mercury is to our own sun. And in fact, if you're living on one of these planets, you would see the other planets the same way we would see our own moon. So this would be a really crazy system to live on. And don't be fooled by these nice pictures. These are artist renditions. We can't see these planets. So they just made up what these planets look like. Nobody knows if they're rocky or if they have water on them. This is a nice picture, but don't take it too seriously. We don't have that kind of information. Proxima Centauri, the closest star to the sun, only 4.5 light years away. So it's not really in our solar neighborhood. Turns out it has a planet, and that the planet is probably in the habitable zone. So that's pretty cool. Also, it's very close to the star. It's only an 11-day orbit. So our planet orbits the sun in 365 days. This one is much closer, but because it's a red dwarf, Proxima Centauri is a red dwarf. So this planet is actually in the habitable zone, probably. Yeah, some people are talking about actually taking this really tiny spaceship, like a cell phone-sized spaceship with a giant light sail, which is this very thin metal or nano material sail, and beaming a really powerful laser at it to accelerate it to 10% the speed of light, and then have it do a flyby of Proxima Centauri to take it, like a few pictures and beam them back to us. This is completely theoretical. Nobody's building this right now, but maybe in a few years people will actually do this. All right, and finally, James Webb Space Telescope. I'm so happy to be able to tell you that this has already been launched because it was delayed many years, and its budget grew and grew. And when the day of the launch came, I turned off YouTube and I turned off everything, and I said, if it blows up, I don't know if I can take it. I've seen the Israeli spacecraft that was supposed to land on the moon. That crashed. After that, I was like, I'm not watching any more launches. But it succeeded. It's now deployed and it looks good. In a few months, we're going to start getting images. So James Webb Space Telescope actually has a really good spectrograph. It's the biggest space telescope we've ever sent to space in terms of the aperture of the mirror. And it works in the infrared, where you can actually see planets much better. The difference in the light that's emitted from the star and the planet. So the planet is brighter in infrared than it is in visible light. So it's easier to actually take a spectrum in the IR. And the idea of James Webb is to actually look at nearby stars, look at their planets, and actually try to measure the composition using these specific spectral lines, right? If you measure a line for oxygen, and at the same time you measure molecular lines for methane, these are materials that usually just mix and generate other materials, right? Methane burns in oxygen. So if there's an abundance of these specific materials in the atmosphere, then you know that it's a biological reaction. And the chemistry we know doesn't create these biosignatures. I mean, that's why we call them biosignatures. And this is what people are going to be looking for now. So this is really promising. So here's my conclusion of the first part. Simple life is common in the galaxy. I don't know what you're talking about. Yes, you ruined it for me. Thank you. So most of Earth's history has simple life forms. You can probably assume that for other planets around other stars, it's probably going to be simple life as well. But it looks like life starts immediately when the conditions are right. There seem to be many planets in our galaxy that can host life. So I think there's many of these simple life out there to find, and we know how to find them. We have tools up in the sky right now that might be able to find them. So I'm very optimistic about this. Right, so as I said before, this is not from the Cambrian era. This is from the late 90s. The book was better, by the way. All right, so any questions about this so far? Kind of making a break now to other things. No? Okay. All right, so what you're really interested in hearing about is intelligent life, right? This is much more interesting than finding bacteria around other places. Although I would say that just knowing that we're not the only place in the galaxy that has any kind of life is super interesting in itself. Intelligent life is probably more interesting. And here it gets a little bit more speculative. Unfortunately, I don't have a lot of good answers for you in terms of science, but it's fun. So why not go into it, right? Even though we don't know a lot of stuff about this. So the first thing I want to say is kind of depressing. The galaxy is super big, okay? It's tens of thousands of light years. So if you think about our planet, we've been broadcasting radio for maybe 100 years, right? So there's a little tiny bubble of 100 light years around our star, and the galaxy is tens of thousands of light years. So most of it doesn't see us, even if it had like super sensitive detectors. And even if some civilization on the other side of the galaxy was broadcasting some sort of radio waves, TV communications, commercials, I don't know what, for tens of thousands of years, it might be long enough for it to reach us, but probably we won't be able to measure it. It will probably be swallowed up by the background radiation, and it would be all noise, and we wouldn't be able to see it. But that's not the only thing we should be thinking about. So if you think about technological advancements, it's been going up on a very steep curve, right? It used to take us tens of thousands of years before we moved from the agricultural revolution to printing press and scientific method, and then it took us hundreds of years to invent like the steam engine and the cars and all this industrial stuff. And then moon landing was only 50 years ago, and internet is only 20 years ago. A lot of people here don't know what it's like not to have internet. So think about that. Yeah, so what I'm saying is it's increasing exponentially, right? Who knows where we're going to be in 1,000 years? We're going to have super advanced technology that we haven't dreamed of yet. So how much time would it take a civilization like our own if we had, like if I told you have 10,000 years to work on it, right? We're talking about going to Mars in the next few decades. What if we have 10,000 years of continuous technological advancement at the rate that we have now? And even if the distance to the nearest stars is tens of light years or hundreds of light years, and you have a ship that can go 10% the speed of light even, or 1%, okay, that's still on the timescales of thousands and tens of thousands of years. That's not a lot compared to the timescales of the galaxy. You guys know what this is, right? Was that it? Futurama, thank you. Okay, good. A representation of each one of the things I've shown so far. That's good. Right, so the Fermi paradox is like this. If some creatures, some intelligent life forms were lucky to be born on a planet, 3 billion years before Earth formed, and they took a few billion years to develop intelligence, and they're still a billion years before us, okay? That time scale is huge. They would be able to colonize the nearby stars, and from there they could just send ships to the other ones and exponentially take over the entire galaxy. So it's kind of like if you have a billion years of exploration with intelligent life that likes to develop and send space probes and sends colonizing ships, why wouldn't these aliens already be here on this planet right now, or at least nearby planets? Even if they started at the other edge of the galaxy, how long would it take them to actually be everywhere and be very visible? So the Fermi paradox kind of says, if that's how it happened, then we should be seeing them everywhere. It shouldn't be hard to find these intelligent creatures, and that's the paradox. So they were kind of talking about this during the Manhattan Project, where Enrico Fermi was working. He was sitting to lunch with these people, and they were talking about aliens, and they were like, but he did these calculations, this sort of calculations I was talking about right now about timescales, and it was like, where's everybody? So it is a paradox. So there's a few ways to think about this. So this is a hard one. Yeah, District 9, right? It's good. Okay, so SETI. Right, so there's actually a big SETI lab in Berkeley. A lot of people are working on actually listening to transmissions from other stars, and the thinking is that if another alien civilization is more advanced than us, they would be measuring all these spectrograms from our planet, and they would say, oh, there's life here. Let's beam a laser directly at them to say hello. And then if we look for that, we might actually end up seeing that. I think it's a long shot, but it's worth listening to. So yeah, people are working on actually listening to space to see if anybody's beaming stuff towards us. There were a few experiments where people actually beamed radio waves into space with like a message. Again, tens of years ago, so can't expect it to reach very far right now. And also, if intelligent life exists very far in the galaxy, it's probably not going to be able to pick up these transmissions because just of the background noise. The further you go, the radiation the radio waves just lose energy. It's very hard to see them. But people are looking for this. So this is an active research. I have friends here in Berkeley who are working on this. Some people sometimes ask me, but it's not a paradox because they are visiting us, right? So I will tell you my brief opinion on this is that all the alien sightings usually kind of look like the most recent Alien movie that came out. So that's kind of makes you wonder about how reliable they are. And also, I think that the fact that everybody today has a digital camera in their pocket all the time, and still nobody manages to get a decent photograph of a UFO, that kind of tells me that it's probably very unlikely that they're actually visiting us. Right. Yeah, we're good. So Oumuamua was a very strange object. It was an interstellar object that came flying through our solar system in 2017, I think. And it had all these weird properties. It was very cool. Like it was very reflective. It had low IR and high visible light radiation. It had these changes in brightness, like it was like a revolving long narrow tube or a flat pancake like that was rotating, and that's why its brightness kept going up and down. When it was leaving the solar system, it actually started to accelerate, or at least its velocity didn't change according to only gravity. So we see that a lot of times for comets, where they eject some gas and they accelerate in a like weird way. But here, nobody saw any outbursts. So they say, why is it accelerating? There was no outburst. A bunch of really weird things. And some people would say, and made this theory that this is actually an alien artifact, that an alien culture just spewed out lots of these probes, and one of them may be directed at our solar system, or maybe just happened to fly through it. And like I said, over billions of years, you don't know where these things end up. Maybe this is what this is. So a lot of people were reminded of a classic science fiction book, which I highly recommend, where the spaceship of the aliens came into our solar system really in a hyperbolic orbit, and it was long and shiny, and it kind of looked like a Oumuamua if you imagine it. But no, probably it's just a piece of nitrogen ice that flew off a planet or something like that. There are a bunch of papers trying to explain the physical properties of Oumuamua. Yeah, the consensus right now is that you can explain all these things without invoking alien probe, unfortunately. But it looks like it, so that's cool. So yeah, so I'm sorry to say there's still no hint of intelligent life in our galaxy, as I said, including planet Earth. Sometimes you would say. But we did get a big chunk of this equation down now. Okay, so number of stars in the galaxy, 200 billion. Fraction of stars with planetary system, order of magnitude 50%. Number of Earth-like planets, there are estimates, maybe 1 in 100, so they're pretty common. Fraction of them that harbor life. Here it's more speculative, but like I said, on our planet, life started immediately when the conditions were right. So if a lot of these planets have the right conditions, let's give it 50% to be like a little bit skeptical. We'll not say 100%. Let's say 50%. Probability to develop intelligence. I'm an optimist, so I say 100%. A lot of other people would say, no, intelligence is actually really hard because, see, it took us billions of years to reach from microbial life to intelligence. So maybe there's a bunch of hurdles you have to get through, and maybe life on a similar planet like Earth would be happy to continue with dinosaurs and creatures that don't develop technology and shoot each other and send off radio waves and all that. I mean, life can continue without intelligence. So a lot of people say intelligence is very rare. And that's one of the explanations. But I'm an optimist. I think that intelligence is so good in terms of, we took over the planet, right? So evolutionarily, it's great. We're doing much better than cows. Maybe, it's us and the COVID. So let's say 50%, right? Okay, in terms of evolution. It's just such an advantage. As soon as something gets intelligent, it takes over the planet. So I think that if we weren't here, a billion years later, some other creature would develop opposable thumbs, right? It's just so good. You have to use it. And the probability of an intelligent civilization to develop communications, again, it's very speculative, but I think that once you have the technology, it's very hard to imagine like a technological species saying, no, we don't care about any of that stuff out there. We only care about what we have. So let's say 50% of these civilizations that are intelligent go and explore the stars. And the last thing is the hard one, right? How much time do these cultures survive? That's the million-dollar question, right? So if you put the numbers and you put our civilization, which has advanced technology for 100 years, let's say, you put that in the equation, what you get is that the number of intelligent communicating species in the galaxies is about 1 in 1,000. So we should be very lucky, right? So that means there's no paradox. It's very easy. All these civilizations live for 100 years and they go extinct, and and that's why there are no other civilizations that we can see. But what if we survive more than a few centuries? We still have that opportunity. If we don't get into a nuclear war, with whatever's happening now in Europe, then maybe we can survive for 1,000 years or 10,000, or why not? Maybe at some point we will outgrow nuclear weapons and climate change, and we will survive for 1,000,000 years. Right. So instead of 100, you put 1,000,000 years here, and suddenly this number starts to become a little bit bigger. If it's 1,000,000,000 years that this culture survived, then yeah, there should be many, many intelligent communicating civilizations. So I think that today, with the information we have about this part of the equation, we can actually say that if you believe that some civilizations survive for a long, long time, then we should be seeing them. So why aren't we seeing them? Here, I'm going to give you some of my opinions, right? This is not scientific. This is just anybody can come up with any excuses or explanations that they want. Maybe they survived just a few centuries, right? We were very close to blowing ourselves up in the Cold War, right? That's not hard to imagine us doing that in the future. Maybe we're just lucky to be first, right? Somebody's got to be first. Maybe everybody's hiding, right? Maybe other cultures just got to this technological level where they figured out that if they encounter another species, they will either destroy their culture or get destroyed by their culture. And they just say, we don't want this. We want to hide. Just close down all the radio waves. We can use fiber optics. That's fine. No more transmissions. Don't want anybody to find us, and that's it. Maybe colonizing space is just really expensive. Maybe we think it's cheap. We think it's very easy. We think we can colonize Mars in 10 years, like Elon Musk believes. But maybe he's wrong, right? Maybe it's way more complicated than anybody thought. Maybe electric cars are easy, but space exploration, maybe it's hard. So maybe we just underestimate how hard it is, or maybe there are these civilizations and they're just in distant parts of the galaxy and we just haven't seen them yet. So I think that 3, 4, and 5 are kind of hard to actually believe in if you say this about every single culture, right? There's 100 cultures, intelligent cultures in our galaxy, and half of them are much older than us. Surely one of them would figure out how to do this and want to do this and go ahead and colonize the whole galaxy. It's very hard to believe all of them aren't doing it. But I'm thinking that maybe kind of a combination of 1 and 2. So maybe some of them existed before us and they destroyed themselves, and some of them, and we're just lucky to be among the few first ones, and we're in this place where we still haven't destroyed each other. So it's kind of the entropic principle, right? Because if we were culture number 2, in the galaxy that did not destroy itself after 1 billion years, we would again not be asking these questions, because the aliens would already be landing here and explaining everything to us, and we wouldn't need astrophysicists at all. So to be having this seminar and to be asking these questions on our own, we have to be the first ones, or at least the first ones not to destroy themselves yet. And that's important, yeah. So that kind of, for me, that makes our position in the universe even more important or more profound if we really are the first ones that haven't destroyed ourselves yet, and we still have a chance not to destroy ourselves. So I think that's pretty deep. So in summary, life started on Earth pretty much as soon as it was formed. Most of the time Earth had microbial life, so we can expect most of the planets that we found that are habitable to have microbial life on them. And we would probably have the tools to detect microbial life, or at least biosignatures. And that's probably going to happen in the next 10, 20 years. And for the more speculative stuff, if any alien species doesn't destroy themselves, and probably should have seen them by now, but maybe we're the first ones not to do that. So that's what I think. Thank you.